today we are going to be talking about scheduling of job shops. And when we are talking about scheduling of job shops, I think you must appreciate what do we mean, or what is the nature of job production, and what kinds of problems exist in the job shop, and what is it that we are trying to address through job shop production. In a typical job shop, what is happening is that a variety of jobs are being produced. That's one thing. And both the nature and the demand of jobs is unpredictable in a typical job shop situation. You can contrast this with batch manufacturing, where in batch manufacturing you are sure about what you have to produce, and you are typically producing those very quantities at predetermined intervals. But the nature of the job shop is that depending upon the kind of jobs which emerge, there is therefore a much greater degree of unpredictability in the job shop. A job shop typically consists of a large number of general purpose machines as opposed to special purpose machines, which would typically happen in an assembly line. So once you have general purpose machines, that means you can handle a variety of jobs on those machines, and therefore the job shop is equipped to handle this kind of variety with a variety of with a number of machines of different kinds. Each job, depending on its technological requirements, demands processing on machines in a certain order. What we are meaning here is that each job, by virtue of its special nature, would require processing on a number of in the sequence of would be different for each job, and therefore what we are saying is that each job is essentially unique in a typical job shop. And jobs will tend to queue before machines, that's one situation, or there may be idle machines and there are no job for that particular machine. So these kinds of situations might occur temporarily in a job shop. Then what we do is, let's try to see what is the objective in job shop scheduling. In fact, there could be a very large number of objectives. We have listed here some of the common ones. For instance, minimize the total processing time or the make span. You know what is the make span? Make span is the total processing time or the time required to complete all the jobs that you are required to produce. So minimizing the total processing time or make span is one common objective. Minimize the mean flow time. The mean flow time actually talks about what is flow time? Does somebody have an idea what the flow time means? We'll define it more formally in a minute in the next slide. But what it means is that if a job comes on the scene at a certain point of time, then it has to wait for processing up to a certain period, and once the waiting is over, then it is processed. So the total time that a job spends on the shop floor, including waiting and processing, is generally known as mean flow time. That is the time for which the job is flowing around on the shop floor, you can say. Okay, that's it. So minimization of the mean flow time is also a very major objective. Minimize the idle time of machines, which is I think quite obvious, because you don't want to unnecessarily keep the machines waiting for no rhyme or reason. Then you want to minimize the mean lateness or earliness of the job. quite often in the parlance of job shop scheduling, we can talk about mean lateness and mean earliness. Although in common parlance we don't tend to use the word earliness, right? It is supposed to be grammatically incorrect. But here you are talking about lateness. So if the job is due at time 10 and you actually make it at the time 15, that means it's actually late. It's late by 5 days or 5 minutes. So that is what we mean by mean lateness. And if it is earlier than what it is scheduled to be, then it's earliness. In fact, that means the lateness of a job can be either positive or negative. If it is positive, that means you are actually late. That is what we normally refer to in the context of job shop scheduling as tardiness. Yes, please.
So why should we mind if the job is early? If we produce it faster and we get it early?
No, it can be produced early, no? It can be.
So why should we minimize the earliness?
We can just be talking about lateness and earliness. So any criterion based on lateness and earliness could be a criterion. What can happen is that you might want to do the job early if there is an incentive given to you. For every 1 hour completed earlier, you get a certain benefit, you get a certain value, and you earn a certain amount of money. Then of course, so it's like completing it early, you get a certain amount of benefit, and doing it late, you might incur a certain amount of penalty. So when you are having this kind of situation, then this would be appropriate. Minimizing the mean tardiness, minimizing the number of tardy jobs. So if you are making, let's say, 5 jobs, you would like to minimize the number of jobs which are actually tardy. This is the situation that can be done. You can try to minimize the mean queue time. That is the amount of time that a job spends in the queue. So one job spends 10 minutes, the other spends half an hour, and so on. So the average time that the job spent is the mean queue time, and you might want to minimize the mean queue time. You want to minimize the number of jobs in the system, because the lesser the number of jobs in the system, it means the more efficient you are. Actually, if there is no job in the system, you've done all the jobs, and therefore it would be a desirable thing to do. So there could be a variety of objectives in the typical job shop scheduling situation. The job shop scheduling problem is supposed to be a very complex problem. Mathematically, to give you an idea of how complex the problem could be, we have a general result which says that if there are n jobs to be processed on m machines, the number of possible sequences is n factorial to the power of m. This is the maximum number of sequences that are possible with n jobs and m machines. Just to give you an idea how big this number can be, you can see, for instance, if the number of jobs is 5, 10, 15, and let's say goes up to 20, and the number of machines is 2, 4, 5, 5 only, in that sense, this particular value of the number of possible sequences for this particular situation is 14,400 jobs, possibility, combinations. With 4 machines and 10 jobs, this number will go to 1.73 into 10 to power 26, just to give you number of possibilities. With 15 jobs, this value will go up to 3.8 into 10 to power 60. It's a very large number, and in fact if you are using even the fastest computer to evaluate one possibility, you can take years for the computer to actually evaluate all possible combinations, right? And you have a situation here when you are dealing with 20 jobs and 5 machines. In that case, the number of combinations that you can land up with 8.5 into 10 to power 91, very large number again, right. So it's actually because of this combinatorial nature of the problem that it's difficult to find a solution to the general NM job shop problem. The only way you can find practical solutions to such cases is through the use of heuristic rules, and it's very difficult to find out an optimum solution except in certain very trivial or simple cases. So what we'll try to look at in this particular lecture is to see some of the situations for which exact solutions are available, and we'll see the kinds of algorithms which are required for solving this particular problem. Some definitions are in order here. How do you characterize a job shop? A job shop is characterized by the number of jobs, that's one thing, the number of machines M, which is the second thing, the number of jobs, the number of machines. Then you can talk about the pattern of arrival of jobs. Is it a static job shop or is it a dynamic job shop? The difference is that in a static job shop, all the jobs are actually available at time 0, and you know the situation, and no further jobs will arrive till you have solved the problem. But in a dynamic situation, what will happen is you have jobs coming, you have more jobs coming, and you therefore have you don't know when a next job will come, and therefore the pattern of arrival of jobs is actually dynamic in character. The objective of scheduling is to minimize the inventory, minimize the make span, minimize the maximum tardiness, minimize the lateness, and so on. These are some typical objectives in this case. And the scheduling rule that is normally used for solving such problems is first come first served, last in first out, shortest processing time, longest processing time, earliest due date, and so on. So you have a number of priority dispatching rules. We will in fact comment upon the various types of priority dispatching rules that are there in situations where you have the general job shop. That means you don't have results very well defined, and therefore for such cases quite often we are content with using or choosing the right kind of priority dispatching rule. Let's define some terms. So if let us say the job arrives on the scene at time AI, AI is the arrival time of the job in general. So this is the time that the job arrives. The job then waits typically, and this is the waiting time of the job is up to this particular point of time. So at this point of time there is a start of processing, and once the start of processing takes place, the total amount of time required will be the processing time required for that particular job. So this Ti will be the time required. At this particular time, the completion, this would be the completion time of the job, and so you have it here. So what we are simply defining is that the flow time of a job Fi is nothing but the waiting time of the job plus the processing time of the job. So flow time is nothing but the waiting time plus the processing time of the job. And another way of looking at it is that this is normally equal to Ci, which is the completion time of the job minus the arrival time of the job. So Fi is equal to Wi Ti plus Ti minus Ci minus Ai. And this is the physical interpretation of this is the time the job spends on the shop floor waiting and being processed. So you have this particular definition for the flow time of any job. We can also talk about due date related criteria, and again what you find is that this is the arrival time of the job, which is Ti, This is the start of processing of the job here. So the job comes here, it waits for so much time, then it starts processing, and then subsequently you have the completion time of the job, which is Ci. And when you are talking about the completion time as Ci, the due date for the job might be something like this, Di, which could be earlier or later than the due date. So we can define job lateness Li as anything but Ci minus Di. So this could be positive or negative as the situation is. If it is positive, it is lateness. If it is negative, it is earliness. So mathematically we can say that job earliness is Ei, which is the maximum of 0 and minus Li, and job tardiness is nothing but Ti, which is the maximum of 0 and Li. So in that sense we can define job lateness, job earliness and job tardiness, because these are also terms which you need to be clear about. Let us now consider the simplest problem and the problem for which some results are available. That is why we are looking at this problem. It is an N1 problem, that is, there are N jobs to be processed on one machine. N jobs, a number of jobs to be processed on one machine. So all sequences for the N1 problem have the same make span. Do you agree with this? What it simply means is that if you have N jobs to be performed and each job has a certain fixed time, so no matter what sequence you choose, the total amount of time required for doing the jobs will be the same. So really speaking, therefore, the make span will be the same for all sequences. So that is not really a criterion for choosing the best value here. And therefore, other objectives are relevant in this situation. And what are these objectives? You can talk about minimizing the mean flow time. You can talk about minimizing the average inventory. Then you can talk about minimizing the mean lateness, and then you can talk about minimizing the mean completion time. It so happens, and we can prove it, that the rule which tries to minimize any one of these also minimizes all the others. That is a significant result. Okay? So it is very much like saying that the rule which does this, we will see which rule does it, will actually minimize these various objectives simultaneously. Let us try to establish a relationship between the flow time f and other variables. What happens is that we had proved that the flow time is nothing but the completion time minus the arrival time of a job, and this is equal to nothing but the waiting time plus the processing time of the job, and the lateness is nothing but Ci minus Di, that is the completion time minus the due date of the job. From these equations it is easy to see that a sequence that minimizes mean flow time also simultaneously minimizes a variety of other things. How? Mean flow time is equal to Ci minus Ai. So what does this mean? Average of mean flow time is equal to average of completion time minus the average of arrival times. Now the arrival times average will be a constant, isn't it? The time for arrivals will be a constant, because that is the time that the jobs came on the scene. So this is a constant. So what it means is that any particular rule which minimizes the mean flow time will also minimize the mean completion time. One. Secondly, if you look at this particular equation here, summation ti's would actually be a constant for any sequence, So what will happen is that a rule which minimizes fi bar or mean flow time will also minimize the mean waiting time. So that's the second result. And here what you find is that if you are trying to minimize the mean completion time of a job, because the due dates are a constant in terms of their total values, the rule will also minimize the mean lateness. So really what you have seen is that a rule which tries to minimize the mean flow time will simultaneously try to minimize the mean completion time, the mean waiting time and the mean lateness. That's what we have proved here, okay. Let's look at the inventory variation for an arbitrary n1 sequence that you have, n jobs in one machine. What will happen if we have the first job, the second job, the third job and so on up to the nth job being completed? What is the average inventory? When the first job is being processed, the number of jobs in inventory are n. Then once the first job is completed, the number of jobs in inventory is only n minus 1 because one job has gone out, and then subsequently for the third job it is going to be n minus 2 and so on. So ultimately when the inventory is 1, when the final inventory is just one job, in that particular case there is only the last job, nth job is in progress, and that's the one which is actually waiting. So what you can see here is, if you were to calculate the average inventory, you can see the vertical strips here, each of these verticals. So time required to process the first job, nt1, then n minus 1 into t2, which is the processing time for the second job, and so on. So this is 1 to the power tn, and average inventory, this is the total inventory divided by the time period t, which is the total time. So you have this. So the average inventory I is nothing but the area, the total area under the strip divided by t. That's what it is, it comes out here. Then if you sum up the horizontal strips, that is these strips, the total area should work out to be the same. So summing up the horizontal strips, what does it show? This is actually the flow time of the first job in the sequence. This is the flow time of the second job in the sequence. So this flow time means this is the waiting time, and then this is the processing time, and so on. So the total area is f1 plus f2 and so on up to fn. So this is nothing but n times the average flow time, and thus T into average inventory is equal to n into average flow time. So what is quite interesting from here is that the average flow time and the average inventories are nothing but directly related to the area under the curve. So if you want to minimize the average inventory, or if you want to minimize the average flow time, how can you do it? The best way to do it is try to minimize the total area under the curve. That's what it is. So how do we ensure that? How do we try to minimize the total time the total average inventory? It's basically something like this. We plotted a graph between the average inventory on one side, so that the maximum value is n, and here the total time is t. We want to minimize the area. How would you minimize the area? Minimization of the area would mean that you should have some such curve here, and this is what the SPT rule will do, the shortest processing time rule will do. That means if we use the SPT rule, we are actually trying to minimize the area under the curve as shown here, and this would actually ensure that you are basically, and if you use the LPT, you will have to, LPT will maximize whatever the SPT minimizes. So the SPT rule now is the golden rule. What is the golden rule? It minimizes the average inventory, it minimizes the mean flow time, it minimizes the completion time, it minimizes the average lateness and the average completion time. So all these criteria, all the 4 criteria that we are talking about. So you can really say that this is something like a 4-in-1 ice cream. One particular rule, that is the SPT rule, for this kind of situation will simultaneously accomplish those 4 objectives. That's what we have tried to prove. Okay. And so this is actually a summary of the final result that we have. The SPT rule, that's the rule that minimizes the mean flow time, also minimizes the mean in process, mean inventory. So it is seen that the shortest processing time rule minimizes the mean inventory, the mean flow time, the mean waiting time, the mean completion time and the mean lateness simultaneously. So this is the advantage of using the SPT rule. Let's take an example and try to see what would be the implication of choosing an SPT rule. So let's say that there are 6 jobs with processing times 4, 8, 5, 9, 2 and 6 respectively. So 6 jobs have to be processed and these are the processing times available for the 6 jobs, and the due dates for these jobs are 10, 8, 12, 15, 9 and 20 respectively. So the final solution is therefore very simple. You follow the SPT sequence, and the SPT sequence means that you take the job which is the smallest processing time. So you take this job which is job number 5. So job number 5 has a processing time of 2. Then job number 1 has a processing time of 4. Job number 3 has a processing time of 5. Job number 6 has a processing time of 6 in that sense. Job number 2 is, for instance, this particular job, this is job 8. It has a the processing time of 8, and job number 4 has a processing time of 9. So job number 4 has a processing time of 9, so we have this particular situation here. So this is the sequence in which the jobs would be done under an SPT rule. So we say that the SPT sequence is this. The completion or the flow times are simple. This job ends after 2. This job takes, so you take the cumulative times. This is 2, then this is 4, which is 6. Then after 6 it is 11. 11 plus 6 is 17. 17 plus 8 is 25. 25 plus 9 is 34. So these are the completion times or the flow times of these particular jobs. The due dates are like given like this for each job, the due date. So 5, 1, 3, 6, 2, 5, and you are given these particular due dates, and knowing the difference between Ci minus Di, you get the lateness values. So the lateness values for this particular example are -7, -4, -1, -3. So these jobs are typically early and these 2 jobs are late for this particular example. So what we are doing is we can look at some of these values and try to summarize the results for this particular case. So the SPT sequence is 513624. The mean flow time is 95 divided by 6, which is 15.833. The average inventory is 6 into 95 divided by 6 into 34. This actually comes directly from the formula that we derived about the total area under the curve for inventory. So the average inventory is 2.794 jobs. The mean lateness is 3.5, the mean tardiness is 6, and the mean earliness is 2.5. So this is how you could summarize the performance of a particular rule, in this case the SPT rule. And what we will do now is we will take another example, and in this example we will see that if we have, let's say, 8 jobs to be done, the processing times for each of these jobs is given and the due dates are given, and the slack times, corresponding slack time is nothing but the difference between the due date and the processing time. So 15 minus 5 is 10. That's how we define slack time. 10 is the due date minus 8, which is the processing time. This is 2, and so on. The important thing is that we will now state some other results without actually going into proofs. But what we will do is that to the same problem, if we apply different kinds of rules, we might apply, for instance, the SPT rule, and the SPT rule tries to minimize, apart from other criteria like mean flow time, average inventory, and so on, so all the other criteria. So the corresponding value of the mean flow time, the weighted mean flow time, the mean lateness, the maximum tardiness, the number of jobs, and so on is like this. Another possible variant of this job could be the WSPT rule, that is the weighted SPT rule. In the SPT rule, we do not assign any weightages to the rule, to the times. So we have weighted mean flow time, if that is the objective. This would happen if you take certain weightages to be applied to different rules. So what you do is you take T1 by W1, T2 by W2, T3 by W3, and so on. So if you are taking a higher weightage, you are actually reducing the value of T by W, so it gets a higher priority in that sense. So that is the weighted SPT rule, and for this is the performance measure. And the implication of the weighted SPT is that it tries to minimize the weighted mean flow time rather than the mean flow. The third rule that is commonly talked about is the earliest due date rule, EDD rule. And in the EDD rule, what happens is, this particular rule will try to actually maximize the job lateness, or it will try to actually minimize the job lateness and the minimum job tardiness in that sense of the term. And corresponding values of the mean flow time, the weighted mean flow time, the mean lateness, and the tardiness and the number of tardy jobs are actually shown here. Then the fourth kind of rule which is important is what we call Hodgson's rule. In Hodgson's rule, the objective is to minimize the number of tardy jobs. Try to minimize the number of tardy jobs. So corresponding to this rule, you have the mean flow time, the weighted mean flow time, the mean lateness, the maximum tardiness, the number of tardy jobs, and the mean tardiness values which are shown here. And then finally the slack. Slack is nothing but the mean tardiness, which is a heuristic. This tries to minimize the mean tardiness, and these are the corresponding values. So what we have basically tried to show here is that just in the case of the SPT we considered the proofs. In the other cases we are simply stating the results without proof. That WSPT will minimize the mean weighted mean flow time, the earliest due date will try to minimize the the maximum job tardiness or the maximum job lateness. Hodgson's rule will try to minimize the number of tardy jobs. Actually, Hodgson's rule is something derived from the EDD rule. What is the EDD rule? The earliest due date rule, which means once you know that the jobs are arranged according to the earliest due date, you will find out the job which is first late, and the job which is first late is then discarded from the scene, and you keep it in the set of jobs called the set of late jobs, and then keep on doing this exercise till this process ends when you have the minimum number of late jobs. So after the N1 problem, that means where you have n jobs now and 2 machines. So we are now considering a situation where there are n jobs, 2 machines, and it's a flow shop situation. If it's a job shop situation, we don't have an exact solution procedure for that particular case. As I indicated to you, we are discussing only those situations for which exact solutions are available. In the flow shop, so what is a flow shop? Flow shop means that if this is machine A and this is machine B, then all jobs will be processed first on machine A, then on machine B, and they won't have any arbitrary sequences. So that's what we mean by a flow shop. And different sequences now have different completion times or different make spans, and therefore unlike the N1 problem, minimizing the make span is a legitimate objective. You see, now for the N2 case, any arbitrary sequence will not actually minimize the total make span. So the rule which is commonly used for solving this type of problem, the N2 problem, is actually the one which is Johnson's rule, and it's easily used to solve the problem. Have you had an exposure to Johnson's rule earlier? Okay. So how we actually solve the Johnson's rule is actually, suppose we have this problem, and the problem is that we have, let's try to solve this problem. Job 1 requires 10 units of time on machine A and 2 units of time on machine B in that sequence, because it's a flow shop. Similarly, job 2 requires 5 on A, 7 on B. Job 3 requires 4 on A, 10 on B. Job 4 requires 12 on A, 8 on B. And job 5 requires 9 on A and 6 on B. Okay? So how do you solve a problem like this? I mean, how would you look at the problem? Let's try to solve this particular problem, because what we can do is, suppose that we have a problem like this. So we are saying essentially job 1, so you try to find out what is the minimum processing time. What you notice is the minimum processing time occurs on job 1. This is the minimum here, and this is also the minimum here. So this figure is the global minimum here. So what happens is that if this particular time happens to be on B, we will schedule this job last. If it happens to be on machine A, then we will schedule this job first. So what we will do is, we have a table in which we can directly say job 1 should be last. So you put job 1 last. We do that here, okay? And having done that, now after this job 1 has been processed, so what we can do is we can cross out job 1 from the list because it has been done. And then from the remaining times try to identify which is the smallest value. So the smallest value is now 4. This is the smallest value, isn't it? So this means that job 3 will now be done first. So you do job 3 here. This is what we do. And then of course this particular job has been scheduled, so you can cut out this job like we did, and from the remaining times again try to find out which is the lowest. So the lowest value now is 5. That means since this occurs job 2, for job 2 so job number 2 is scheduled here. Once we have scheduled job number 2, we can cross out job number 2 because these are the 3 jobs which have already been placed. And look at this particular situation here. What is the minimum now? The minimum is 6. So job number 5 should be scheduled last in the available slot. So job number 5 should be scheduled last here. Okay? And once it has been scheduled, then we can cut out job number 5 from the list. And then of course the minimum is 8. So job number 4 should turn out last. In fact, there is only one slot, so it goes here. So what have we been able to find out? And then of course all the jobs are now assigned. This particular procedure that we have just followed is called Johnson's rule. And what you find is that by applying Johnson's rule, we have been able to determine a sequence 3, 2, 4, 5, 1. And this particular sequence ensures that the total make span or the time required for doing all the jobs is actually minimum. So you can find out exactly how the time would be a minimum. What we need to do is simply we need to draw a Gantt chart to be able to determine this particular value. How is it done? In fact, it is done in this manner. You know 3, 2, 4, 5, 1. So job number 3 has a processing time of 4. So we can go from time 0 to 4, and this is the time required for job number 3. So job number 3 on machine 1 will go from time 0 to 4 in that sense of the term. Then you have job number 2. Job number 2 has a processing time of 5. So 5 plus 4 is 9. This is time 9, and this is processing sequence 2. So after 3 we process job number 2, so we get 3. Then for 4, for processing time for job number 4 is 12. So 12 plus 9 is 21. And this is actually job number 4. And then subsequently when job number 5 is concerned, job number 5 would require a total time of 9. So this will be 30. And this will be 5. So we have 3, 2, 4, 5, 3, 2, 4, 5 and 1. This is what we are doing on machine A. And what is the processing time for 1? For job number 1 requires 10 units of time, so what you'll have is 40 here, and this is 1. So all that we know through a Gantt chart is what is the time that the job sort of enters, which job enters, job number 3 from 0 to 4, job number 2 from 4 to 9 and so on. So 3, 2, 4, 5, 1, and it comes out at time 40, right? However, in order to tell us the complete time at which this job will be over, you have to talk about processing on machine B. So processing on machine B is done in the same sequence. So what happens is really that as far as job number 3 is concerned, it has a processing time of 10 on machine B. So 10 means 4 plus 10 is 14. So you are going to be somewhere here, right? This is 14 and this is 4. Obviously up to this particular time, from 0 to 4, this machine B is going to be idle. And 4 to 14 is the time required for job number 3. So this is job number 3 which is actually being done on, so it requires 10 units of time here. Then we are talking about job number 2. When you talk about job number 2, it has a processing time of 7. So what's going to happen? That this job, which is actually over at time 9, will have to wait up to this particular time, because the machine is not available during this particular time. So then at time 14, you can start processing job number 2. Job number 2 will take time of 7. So exactly at time 21, you will have job number 2, which will be processed from 14 to 21 on this particular case. Then you take job number 4. Job number 4 will require a processing time of 8 units. So what happens is, this is at 21, this is at 21, so the job doesn't have to wait now. So what is going to happen is that job number 4 will require a processing time of 8, so it will go up to 29, so it will be over here. And this is now job number 4. So 3, 2, 4 and at time 21. Then what's going to happen the next one? This machine is over at 29, but this job has not yet completed its processing on the first machine. So this will be a situation where the machine is going to be idle. So this is the machine which is idle during this particular point of time, and at that particular point of time, at time 30, this job number 5 is going to be available, and then it will take on, that means it is available at time 30, and from time 30 onwards till that means we are now talking about job number 5, so the total processing time is now 6. So up to time 36 you will go on up to here, let us say, and this is now job number 5. And then we talk about job number 1. Job number 1 is being processed till time 40, whereas this machine will again be idle up to 40. So this particular processing time can only produce after can be done only after 40, and as far as job 1 is concerned, it would actually be over at 42, and this is therefore job number 1. Now you have the complete picture. What it shows is how the two machines are going to be loaded with different types of jobs according to Johnson's rule. What we find is that the completion time or the make span for this job is now 42 units, and this is the make span, and the guarantee that we have from Johnson's rule is that there is no other sequence which will reduce the time required for doing all the jobs in lesser than 42. That is the guarantee. So this is how you can use Johnson's sequence and the notion of Gantt charts to actually identify the total time in which the jobs are going to be done. So we know that the make span is now 42 units. What we can now try to explain is in fact this particular situation where you have the N3 flow shop situation. That means we are now talking about N jobs, 3 machines to be processed on a flow shop. What does it mean? That there are 3 machines A, B and C. The processing has to be done for the N jobs first on A, then on B, then on C. So it's a flow shop situation. And this is the kind of situation. So what would happen is something very similar. Actually this rule that we are talking about now is called Jackson's extension of Johnson's rule, right? Very interesting. It's like 2 brothers who have solved the same problem. So what you have is that the first job requires processing on A, processing on B, processing on C. Similarly 2 requires processing on and so on, 3. Now what happens is that in case there is dominance meaning that let's say the minimum of the time on A, the minimum of the time on A is 8. This is the minimum time on A. And the maximum time on B, which is the middle machine, the maximum time is also 8. So when the minimum on A is greater than or equal to the maximum on B, this is said to be dominance. So what can happen is that machine B could be dominated either by A or by C, and if that happens, like this is a dominant situation, then you can convert this problem into a equivalent Johnson's rule problem and solve. How? You can take A plus B together and B plus C together. That means you can take 2 fictitious machines, A plus B and B plus C. And then once you have done that, you can look at, that means what we are trying to say is that we can combine A plus B and B plus C, we will have 2 columns, and we can solve the same problem by using Johnson's rule and get the same sequence, and then try to apply the same sequence now to 3 machines. So it will be a Gantt chart which will have 3 machines, and it will give you the minimum make span for this problem. However, it has been seen that even when dominance does not exist, that means here what you find is the minimum is 4 and the maximum is something else which is 8. So there is no dominance here and no dominance here. Even in such a situation you can combine A and B and B and C. You will still have 2 fictitious machines, solve it, and the general conclusion is that the solution is generally found to be very close to optimum, even when dominance does not exist, although it's not optimum in general. So that is what you tend to find in this kind of situation here. Yeah, so as far as computations are concerned, all that you need to do is the time required for A and B, you put it down here, the time required for B and C, put it down here, and do complete this table. Once you have this table completed, solve it exactly like a Johnson's rule with 2 fictitious machines, and then the sequence which you determine as a consequence will in fact be the one which will try to minimize the make span. So you can just solve the problem in this particular way. This can apply both to the case when there is no dominance and also to the case when there is dominance, both the cases that we considered. Only thing is, when there is no dominance, then you have this particular situation. The next problem that we can solve for this particular situation is a 2M job shop situation. A 2M job shop situation means that there are 2 jobs, there are M machines, and there is a job shop situation. That means the sequence is the same. This problem can be solved graphically. It's a very simple graphical solution. For instance, what you can do is you can plot the 2 jobs on 2 axes. It's a 2 job situation, right? So you can say job 1 and job 2. in this manner. And then what can happen is that each of these jobs can require processing on different machines, right? So you can have, for instance, if suppose there are machines which are like B, A, C, D, let's put it this way. That means what we are saying is that job number 1, this is the time required for processing on machine B. This is the processing time required on machine A, and so on. So we write down these times in the sequence in which the processing is required. This is for a job shop. And you can also find out the same thing here. For instance, you might say that this is A, then this is C, then this is D, and then this is B, in that sense. So this is the sequence in which job 2 requires processing on different machines. So it's a general job shop situation. What you then do is something very simple. This is A and this is A, so you can mark out this area, let's say here, and call this as A. Then as far as B is concerned, you can mark out this area here and look at this area and call out this B. Then as far as C is concerned, you have this area here and this area here, and this is the area that you can mark out as C. And as far as D is concerned, you have this area, and then you have this area here, and you have this area here. So this is, let's say, D. And what are we trying to achieve? We are simply trying to say that as far as these jobs are concerned, you will finish here and you start from here. Okay? So you have this particular situation, right? Now why we have put this time is that here in this region, both job A, that is job 1 and job 2 are both requiring machine A. So this is not possible. Similarly here so we have to basically avoid these regions. And what we have to do is determine a path from here to here. So the path can possibly be, in this case, in fact there is no difficulty, we can go from here and ultimately come here, right? So as far as path is concerned, we have got path number 1. You can also look at the other possibility. You can say, for instance, you can come here, you can go here, and then take a path like this and come here. So this is path 2. The basic idea here is that a path can consist of either a horizontal movement or a vertical movement or a 45-degree movement. A horizontal movement means job 1 is being processed. This means job 2 is being processed. This means both are being processed simultaneously. So you would then, after having enumerated a couple of paths, be interested in that particular path which will minimize the total distance. So by looking at this diagram, you can possibly identify, like in this case, this is the shortest path. So this is the procedure that can be followed for solving the 2M job shop problem. In practical solutions to big job shops, you use a variety of dispatching rules. A list is here: first come first served, SPT, EDD, slack, random, least remaining processing time, minimum ratio of slack time to number of operations, last come first served, least dynamic slack, and so on. So what we are simply trying to say is that what is normally done is that through a process of simulation, you try to identify what is the best you can do, and then try to take that particular scheduling rule which gives the best solution. So let's try to summarize what we have tried to do in this lecture. We have looked at the complexity of the job shop scheduling problem. We have looked at the N1 problem, where the objective was not to minimize the make span, but to consider average inventory and other things. The N2 flow shop situation, Johnson's rule was a solution for this case, N3 problem 2 could in fact be solved by a variance of the job shop scheduling problem. 2M job shop problem can be handled graphically. General job shops and simulation could actually solve this particular case. So I think with this we conclude our discussion on job shop scheduling. Thank you very much.